So, hi, good morning. I hope you're enjoying your stay here, at least in the last hour. My twin was at the reception. Now I'm here. So we are like two people. It's not the same person. The one that's doing the reception, the one that's teaching the SLU. Don't think that we're that kind of organization. We're not. So what I'm going to teach you today is I'm going to teach you about metrics. Why are metrics important, and particularly metrics for regression? You need metrics to evaluate models particularly, and what you need to evaluate is how well your model is fitting to real world data and how your model is really generalizing for the population. So we are going to look here a little bit about those metrics and how can we just calculate those metrics, how can we evaluate them, and how can we use them in data science. So metrics assess the performance of your training models, basically, and you interpret the metrics to allow to see which models are you going to select and which models can you choose and how can you compare between models and which ones are the ones that were trained better and how they generalize to the population. So this is the overview of what we are talking in this session. So loss versus metric, the comparison between these two concepts. We are going to talk about mean absolute error, mean squared error, root mean squared error, the coefficient of determination, which is the R squared, and the adjusted the R squared, and how can we use these metrics to evaluate models. Why? We are going to skip through all these steps because these have like tiny little changes between these metrics that they are important, and you are going to see how what's the difference between them. And this is for continuous variables. These metrics that we are speaking here are for continuous variables, which we are measuring a continuous target. Remember yesterday from the linear regression, we had the points where we wanted to fit like the straight line, and we had the classification when we have like zeros and ones for the binary classification. These ones that we are speaking are for just evaluating models where we are fitting that straight line and where we are seeing the difference between the points and the line that we have estimated. Okay, loss versus metric. Basically, loss is a function that your model will optimize. So you give a loss so that your model will try to minimize this function and optimize this function. And metric is a function that you want to minimize to evaluate the model itself, not on the development of the model. Sometimes it can be both, but mostly for evaluating after training the model, where your model will behave when you unleash it on real world data. Sometimes, in some cases, specific cases, they can be both, okay? The same function can be a loss and the same function can be a metric, okay? Mean absolute error. So imagine that we are fitting a straight line over some points. I could draw, but we don't have the time for that. So imagine that we have like a some points where we are just fitting this line. We want to measure what's the difference between my predicted point and the real point that we have on that, imagine a 2D graph. That's one of the ways that we can measure the difference between what we are estimating. So we have developed some parameters, we developed something to represent reality, and we say, okay, this is my estimation. What's the difference between the reality? And mean absolute error basically can tell you that. What's the mean absolute error? 1 over n, dividing just the absolute between the y, the real y, or the real target, and the one that you have predicted. So imagine that, why is the absolute value? Because if you have a straight line and you sum all the difference between the points and the line, if you sum all of that, that will be 0, because that will be like the residuals of what you're estimating. So you just absolutely, you put the absolute value so that you have like a metric where you can say, okay, this is the sum of this is the errors, is how much I am deviating from reality. And you can deviate that in a way like positively or negatively, because you can be overestimating or underestimating your hypothesis, okay? So this can work also as both a metric and a loss. And it's not sensitive to outliers because there is another metric That's mean squared error, and this is sensitive to outliers because you are squaring the difference. You see the difference between the mean average error and the mean square error? In the average error, you have the absolute value. In the square error, you square it. Why is this sensitive to outliers? Because you are giving a penalty when the values deviate too much from the line that you have estimated. Are you visualizing the line? I'm trying to bring some example here so you visualize like the example of what we are talking about. And when you square it, imagine that you have a difference of 5 points between what you estimated and what is the real value. For example, heights. Your model is estimating that someone with some characteristics is 170 meters tall, and the real value is 175 for the person with those characteristics. The difference is 5 centimeters. If we have an absolute value, 5 centimeters. If we have a squared value, 25 centimeters of difference. That's why the outliers will be much more overweight in this metric. Okay. Root mean squared error, just give a square root to the number, to the mean square error, and boom, it's done. Okay. So this also is sensitive to outliers because of the same reason, because you are basically using mean square error. Okay. Coefficient of determination. This is an important one. Basically, when you develop something with that has like linear function, when you're using a linear regression, particularly, everybody will ask about your coefficient. And the R2 is used for a lot of examples around several industries. For example, one of the things that has been using R2 since for a long time is in finance. When you measure the difference between stock market returns, R2 is one of or the correlation between one specific asset and the total stock market, R2 is used there. And why is R2 important? You may ask, and it's a valid question. See here the formula in this part, like the MSE, where you have the Y value and the predictive value. Remember that this is mean squared error, what we talked about with the square difference. And here is the same thing, but you're calculating it between the real value and the mean. So you are saying, what is the difference of my model and if I just predict the mean of all values? So I'm trying to see how my model will deviate from just a random mean model that exists somewhere that is super simple. If I ask you, what's the average height of a male in Portugal? And you say something like 180 meters, 179 meters, something like that, we could average the predictions of everyone. If you say that, if your model can't beat this mean classification, your model will be worthless because you aren't fitting a line that's better than just the mean variable, the mean prediction. And look that if the error of the predicted model is the same as the mean, this will be 1, so your R squared will be 0, basically. So you have no quality in your prediction, and doing the mean value will be just as useful as developing that model. Adjusted R square. So R square can be a little bit tricky because you can add a lot of features and R squared will always increase. So you are saying, okay, I have a fantastic model because I have 10 million features. That's wrong. So because you are just feeding more and more stuff, and that will be worthless or simply practically worthless. But adjusted R square just basically can, it has some ways of penalizing the number of predictors in a model, and this can be really useful for like comparing models with different number of predictors, because in the adjusted R square you can say that if you just give another predictor, for example, for the height example, if you have age or something like the parents' origin, something like this, I'm making this up, and if you add another variable that that will be like correlated or something like that, but if you give another variable that will contribute to the R squared will always go up, okay? So if in adjusted R squared, this doesn't happen because adjusted R squared penalizes for the number of features that you have in the model. So, yes?
What's K?
Oh, K is the number of features that you have.
Then what's M?
It's the number of rows, basically the number of examples. So with what we are saying here is when K is too high, it's going to penalize this model, okay? Okay, using this metric. So we have trained the model on some specific population. You don't want to measure your metrics on the specific population. Why is that? Compare the example of using the same function as a loss and a metric. So use that as a loss. That is the objective function. You're trying to minimize that loss, and then you are measuring on that loss also because it's the same function. That's cheating. Don't do that. And don't do it where? On the train, particularly on the train model. In the validation, you can do it, but not on the train model, because the train model will typically be where you will get the features and you'll get the signal that will predict something. So you don't want to measure in that. Okay, the validity of your model. If you are training something for the population of Sweden, for the whole population of Sweden, and you want to generalize it to the end of the world, to the rest of the world, not to the end of the world, sorry. But if you want to generalize it to the rest of the world, you don't want to do that because there are some particular things about that population that will not generalize for the rest of the world, right? So you need to have this balance between your population, and you have to make sure that the difference between these two sets, train and test, because the test set is the test that you haven't fed your models with this data, so your models haven't seen this data. They have to be balanced. They have to be like the same population. They can't be biased, so that you have like a fair and square error metric. Remember what we talked about in the formulas from the other slides. You have to have a fair metric and a fair way of evaluating how your model will generalize to the real world, not on your training data, okay? So this is basically the process of developing some training set data. You will train your model here, you will feed your parameters or parameters here, and you'll just test it on the set that's not included on a training set, okay? So you're bearing with me? Sorry.
You're saying that the feed on the training set doesn't have an importance?
Sorry?
The feed on the training set.
It has an importance, but you can't evaluate the metrics in the real world there. Yeah. You can say that for forecast. No, not even for forecast. For example, if you're saying that your metric, you can be overfitting, which will come in the next lectures, but I'll try not to to say too much about that because we'll talk that in the next SLUs. What? Okay, it was yesterday. Sorry, it was my twin yesterday. It wasn't me that was here. So, yeah, because you might be think about this like this way. If your training set, if you're just overfitting because you are developing a line, you can fit a model with a lot of polynomial features, and it will do just like this. Instead of doing this line, it will do this.
But that's
right?
From the extreme, you are fitting like 100%.
You are fitting 100% on the trade data, but that model will not be useful in real world, right?
Yeah.
It will only be useful for that data, and that particular data may not happen again, for example.
But imagine the opposite case. The fit is very bad. It would also be worthless, right?
It would be worthless, yeah.
So if you want a mean between those options.
You don't want but you want to look at, because if the validation feature is okay or is good, the train feature it has a high probability of being okay also, okay, because you are training on something. It is really rare if you can train something on a data set and you are going to apply it on a test set, and it will be much higher, the accuracy score will be much higher on the validation set than on the training set.
Getting good metrics on the training set is a necessary but not sufficient condition.
Okay, that's it. Thank you.
Yeah, this guy can sum it up pretty much. Thank you.
Training. Could you actually repeat that?
Good performance on the training set is a necessary but not sufficient condition.
Perfect. Yes.
You show the split of the training set between of a data set into training and test set.
Mhm.
Is that the proportion that you suggested? Like
No. It's
large training and small test set.
normally it's larger. The training set is larger, but it can be. There isn't. This is kind of a controversial issue because there isn't like a state-of-art proportion that can be used to test size, but you can use 20, 30, 40%. Normally between those values, it's what you're using, okay? So you can use the metrics on a holdout set to choose the best estimators. So this is one of the things that you are looking for in a holdout set, which is the test set. You want to compare all the metrics on that set to choose what is the best estimator that you are getting. Okay, so comparing this, for example, from the case that you were saying, we have a mean square error of 3.32, but when we are looking at the holdout set, we have the double of the error, okay? So more or less. So the mean square error is just double because we are not looking at the training data where the parameters were fit, okay? So we are looking at new data that has a new reality, and we want to measure how well our model will be in the real world. And comparing between the models, we are using two models here. If you can see, we are using the regression estimator and also the linear regression estimator that is the mean square. Sorry, the SLU regressor. I wasn't looking at this. So it's the gradient descent and the closed form that Katerina told yesterday. She thought about two ways of measuring linear regression, remember? She told about the ways that you can do gradient descent, right? And she told about the closed form where you use the ordinary least squares. So those are two kind of things. That's why the mean square error is similar between them, but it is not equal. So see that how can we use the best estimator using the holdout set, the test set? We are minimizing the error because our interest is to have the least error possible on the validation set. Okay, because that's where you are going to apply your model. That's where, in the real world is where you're going to apply your model. Of course, the training set is important also. So cross-validation, okay, cross-validation will be pretty important also because if you are using one test set, there is a possibility of also using a bad test set for some reason. So the more you average through different test sets, so you are training on some test set and using a test set, this experiment done multiple times, okay? With k-fold cross-validation, you basically train on this part and test on this, and then you train on this one and test on this. You see how it may average the error for more generalization because we are using different data to get to some kind of function that may not overfit the training data, okay? So you want to avoid overfit because if you avoid overfit, when you get the model into production, your model will behave much better. Okay.
Then you have a different test set that's just the train set.
No, you have a different test and train set. You train on different, see here, you are always training and testing with different samples to average the error between all of them.
Oh, okay, so in that way, you merge both sets. You don't have a train and test set, you just have the whole data set and you do that.
Yeah, you have the whole data set and you start to train. You first divide it. Imagine this is the first experiment. You have like 4 buckets to train and 1 bucket to test. And then this test set will be a training set on the next experiment. So they are also changing. The train and test set is always the same from the beginning, but they are interchanging between them inside the experiments, okay?
In critical applications, you'll leave another test set.
Sorry?
In a critical application, you'll do all of this and we'll leave another test set out.
So just for the sake of how much my model will generalize, basically. So trying to minimize the error as possible. I have to, okay. So this is an example of cross-validation. We are just using the cross-validation here to just see, this is using mean average error. That's why it's negative, because it's not the absolute value, it's the average error. And you are using it to minimize the error also, okay? So you choose the model that minimizes your error on the test set, okay? So recap. So some of the mostly used metrics are computed directly from the error of our samples, the mean absolute error, the mean square error, the root mean square error. The coefficient of determination, the R2, is used to measure how well does your model behave when compared with just a simple mean estimation. So the most simple model that you can think of, which is estimating the mean for everyone, okay? And these metrics are used to perform model selection based on how good they perform on these unseen data. So the test set, the data that hasn't been given to the model. If the model already knows that, it will not be new for the model, okay? And I think that's it.
No more.
Okay.
Just so you're free. Okay, so Katerina, who was supposed to give this presentation, is sick this morning, and so he prepared and gave this in all of about 1 hour. So much appreciated. Very good. He's almost as smart as his twin brother.
Much.
Sorry. Yeah, just one more thing about just to reinforce some things that he was saying here. One of the most important reasons that you want to have multiple test sets is like the most evil thing you could possibly do in machine learning is just try to maximize one metric on one test set. Okay, that is just a sure way to overfit your model and then make sure that it does not generalize when you put it into production. And that is a hugely important thing to avoiding being like, hooray, send it up to the board that I have this 99.99999 whatever metric. And then you put it into production and the business crashes and burns. Because basically all you did was play a Kaggle game to win your one test set that you chose. Okay, so this cross-validation right here of picking lots of different test sets and seeing how well your model generalizes in multiple cases, not just one. Because your model one case is not a generalization. You cannot evaluate the goodness of a model on one test set. You just can't do it, okay? So now that you're all sufficiently scared, hopefully, go do something.